Okay, so we were discussing the speed control of DC motors. So first of all, we will consider DC shunt motor, right? Uh, so before we start the discussion on this speed control method, let us see what this speed control means. Okay, so what do you mean by speed control if someone asks? So how to describe it? So the term speed control means the intentional variation of speed as per our requirement. Okay, it may be manually, that means we can control the speed either manually or automatically. Okay, so speed control is the intentional variation of speed as per our requirement. Either we can do it manually or automatically. Now there are some other way of changing the speed. That means the speed can change in some natural way. Okay, let us consider our home used fan. Okay, where after certain days we will see that some dark particles will uh, get deposited on the fan blades, and thereby reducing the speed of the fan. So this reduction in speed is not included in the speed control of any motor. Okay, so that is not some kind of speed control. Speed control means intentional variation. Consider the movement of train from one station to the other. First of all, it will accelerate, then it will run with a uniform speed, which is known as free running. Then when the train approaches the next station, it will reduce its speed, and then it gets stopped at the next station. Okay, so that is intentional variation depending on the situation. Okay, is it clear? Anyone having any question or doubt?
No, sir.
What is so here we will consider only DC motors, and in DC motors we will consider only shunt motors and series motor. Okay, so DC motors are most suitable for wide range speed control and are therefore indispensable for many adjustable speed drives. So ASDs, these are called adjustable speed drives. What is the meaning of this? That means depending on the load condition, the speed can be adjusted. Okay, suppose consider uh, uh, some elevator. Okay, whatever may be the load, the speed remains fixed. Okay, now consider some uh, blower. Okay, so it can the speed of the blower can change depending on the amount of load it has to blow. Okay, so in this way, these type of applications are called adjustable speed drives. As per our requirement, we can change the speed of the motor. Okay, so DC motor can be used for those kind of applications. So here consider this schematic diagram of a DC shunt motor. We can see here Vt is the applied voltage or the terminal voltage, and IL is the load current or line current drawn by the motor depending on the load condition. So this IL will vary if the load changes. IA is the armature current, and EB back EMF, RA armature resistance, ISH that is field current, we can denote it by IF, the symbol IF also, and RSH that is the shunt field resistance. Okay, so here the speed of this DC motor can be expressed by this equation. We know this omega m, speed in angular, this is the angular speed in radian per second, which is equal to back EMF EB by Ka phi. we know the expression of EB is equal to Ka phi omega m. So from that we can write omega m equals to EB by Ka phi, and EB can be expressed as Vt minus Ia Ra. We know this equation very well. Okay. Where Ka is the armature constant is equal to Pz by 2 pi A, and phi is the field flux per pole. Now if we observe this equation very carefully, then we can see there are three variables. Vt, the terminal voltage, that we can vary to change the speed when Ia and phi will remain constant. Next we can change the armature current keeping Vt and phi constant. Then also this omega m, that is the speed, will change. Or we can change flux phi keeping Vt and Ia constant. Then also we will get this variable omega, that is the variable speed. Okay. So from this equation we can conclude that there are three possible way of or possible method of speed control of DC shunt motor. Okay. So first of all we can change the terminal voltage. So first method is variation of the armature terminal voltage. Second method is variation of resistance in the armature circuit. So though we are saying that armature current is the variable, so actually we will change this armature current by varying the armature circuit resistance. That means we will introduce one resistance which is called the external resistance, or RC, the controller resistance. Okay, that will be added with this armature resistance, and we can change the value of this Rex, that is external resistance or controller resistance. Okay, so by changing the value of the external resistance or controller resistance, we will be able to change the armature current, this current. Okay, then we will get the variable speed. Okay, so that is the second method, variation of resistance in the armature circuit. And the third method is variation of the field flux. That we can do by connecting one external resistance in the field circuit, and varying that resistance we can control the field current. Now we know that this field flux is a function of field current If or ISH. So if we change this field current, this flux will change, and we can see from equation 1 that the speed is inversely proportional to flux phi. Okay, so these are the three possible methods. Any question up to this?
No, sir.
Okay, let me check whether all of you have joined or not. So 92 only. Okay. So let us consider the first method, that is speed control by varying the armature terminal voltage. Okay. So in this method, what we will do, we will change the terminal voltage or applied voltage keeping field flux constant. Okay. Now from the circuit diagram, you will be seeing that the voltage, whatever voltage is applied across the armature, the same voltage is applied across the field winding also in case of DC motor, shunt motor. Okay, so if we change the terminal voltage, the applied voltage across the field winding will also change. Okay, then how to get fixed, how to keep fixed the field flux? Okay, that is one question. So in that case, we will be requiring a separate voltage source for supplying the field windings, okay, which will remain fixed, and it will keep the field flux constant. And this type of control, that means this armature terminal voltage control, is very effective and economical also for driving a constant load. Okay, so load torque TL will remain constant. That kind of application will be I mean when the load torque remains constant, there only we can apply this kind of terminal voltage control of method of speed of DC shunt motor. Okay. Now let us see how this speed will vary when the terminal voltage will be varied. Okay. So first of all, the speed equation is given by this equation, that is equation 1. So omega m is equal to Vt minus IaRa by Kfi, that is actually back EMF by Kfi, and the torque equation is T equals to Kfi Ia. Combining these two equations, and for that we have to eliminate the armature current Ia. So eliminating armature current Ia from both the equations, we can write this expression, that is omega m is equal to Vt by K phi minus Ra T by K square phi square. Okay, so here this is the relation between the speed and torque. Okay, so from this relation we will be able to see how the speed will vary when the terminal voltage is changed, keeping the load torque constant. Okay. Now we can see from equation 3 that it is a equation of straight line. If we compare this equation with uh, generalized straight line equation y equal to mx plus c, this is a linear equation, that means equation of a straight line. So here we can compare this equation and this equation, and from by comparing these two equations we can conclude that the relation or the characteristic of this speed torque of this shunt motor will be a straight line. This we have already seen while discussing the torque speed characteristic. So now if we change the voltage, what will happen? Consider this diagram where different speed torque curve at different voltages are shown. Okay. So first of all, let us consider when the voltage is Vt1, that means the terminal voltage is Vt1. In that case, the speed torque characteristic is given by this line, and this line is the constant load torque line. So this intersecting point of these two lines, that is speed torque characteristic and the load torque characteristic, will give you the stable operating point. So when this Vt1 voltage is applied and the load torque connected to the machine is TL, the machine will run with a speed of omega m1. Okay. Now if we decrease the voltage from Vt1 to Vt2, what will happen? For Vt2, the speed torque characteristic is given by this straight line, and we can see the stable point of operation is this point, because this line and this load torque line will intersect at this point. So this is the stable point. Okay, so the speed reduces from omega m to omega m1 to omega m2. So the motor will now run with a speed of omega m2 and so on. Okay. Is it clear to everyone?
Yes, sir.
Now the question is, can we in this speed applying applying more voltage, I mean a voltage which is greater than the rated voltage. We can see from this plot that the speed control method, this method of speed control is used to decrease the speed from rated speed. That means we can operate the motor with a speed which is less than the rated speed. Now my question is, can we increase the speed above base speed by applying voltages more than rated voltage?
No, sir.
Actually, no. The answer is no, because if we apply a voltage more than rated voltage, then what will happen? It will affect the insulation of the winding, armature winding, because the armature winding is already designed for a given voltage. So to get higher speeds, if we apply voltages more than rated voltage, then this insulation may get damaged. So in that case there will be a short circuit and the whole motor will get damaged. Okay, so we cannot get a speed greater than base speed or rated speed by this method of voltage, by this method of speed control. Is it clear?
Yes, sir.
Now in this method we can see the speed control is done with rated current. Okay, and since this is a shunt motor and we have applied one separate voltage source to excite the field winding to keep the field flux constant, that means we will get uh, a constant torque. Okay, because we know torque is equals to kt phi ia. So the motor is running with constant armature current and with constant field flux, and this kt is constant for a given motor, so we always get a constant torque. So this is a constant torque drive. That means up to this base speed the motor will always generate a constant value of torque whatever may be the speed. Is it clear? You can see these are the different values of speed. So for all speed values we will get a fixed torque. So we a constant torque drive is obtained, okay, by this method of speed control. Now the power. Here torque is constant but the speed is increasing. Okay, so if we multiply this torque value and this speed value, that is omega, we will get this power value. So since speed is increasing, so power line as this, which is not constant, it is increasing with a fixed rate of increment. So that means this method of speed control we will get one constant torque drive but not a variable power drive. Okay, so by applying this method one constant torque drive is formed or a variable power drive is formed. Is it clear?
Yes, sir.
Yes.
Okay. So please note down this question. Why speeds above the base speed is not possible using supply voltage control of DC shunt motor? this question I have already discussed. Okay. So next method is Ward-Leonard method of speed control. This method is actually some kind of advanced method of speed control of DC shunt motor. By this method, we can apply both terminal voltage variation as well as field flux control method of speed control also. Okay, so here we can increase the speed above base speed as well as we can decrease this speed above below rated speed or base speed. Okay, that means we can have a wide range of speed variation by applying this method. So this is the schematic diagram. See, there are 4 machines. This is the target machine whose speed is to be controlled. This is the generator which will generate some DC voltage, and that voltage is applied across the armature terminal of the target motor. This DM, which is normally we use some induction motor. See, 3-phase AC supply is given. So this is basically a 3-phase induction motor which will act as the prime mover. That means it will rotate the rotor of this generator. That means mechanical power is supplied by this induction motor. Okay, and this is another motor which is a shunt motor. Sorry, this is another generator which is known as the exciter. The output voltage or the generated voltage of this exciter will be fed to the field windings of both this generator as well as this motor. Is it clear? First of all, try to understand the function of each machine. Then I will discuss the procedure, how the speed is varied. This is the target motor whose speed is to be controlled. That is fine. This is the generator whose induced voltage will be applied to this motor. This induction motor will act as a prime mover to this generator as well as this exciter. Why it is called exciter and why it is called generator? Because generator will generate some voltage that will be given to the armature of the motor, and this is also a generator, but we are using some different name than this one, because this will excite the field winding of this generator as well as this motor. That is why it is named as exciter. Is it clear? This machine and this machine both are DC generator. One is used to supply voltage across the target motor and the other is used to supply the field windings of both this generator as well as this motor. And this AC motor, which is normally 3-phase induction motor, is used to drive the rotor of both this generator and exciter. Is it clear?
Yes, sir.
Anyone having any doubt?
No, sir.
Okay. So now how the speed of this motor will be controlled. First of all, let us consider we are going to control or vary the speed below rated speed. Then simply we will control this voltage only. The voltage of this generator, that means the induced voltage of this generator, can easily be controlled by varying this rheostat, that is the field current of this generator. Okay, So we can change the output voltage of this generator and we can control the speed of this motor, keeping all other things constant. So that is the speed control of this motor below rated speed. Okay, now if we want to control the speed of this motor above rated speed, then we have to apply field control, because speed omega m is inversely proportional to phi. So we need to control the field current of this motor. Okay, so field current means which is flowing through this line. So we can control the field current using this rheostat. Okay. So initially fixed voltage is applied by varying this rheostat. Fixed voltage is applied across the field winding of both this generator as well as this motor. Then we can control the voltage, generated voltage of this generator using this rheostat, or we can control the field current of this motor by controlling this rheostat. Okay, if we use this
So you are not audible.
hello,
Yes, sir.
hello,
Yes, sir.
hello.
Voice is breaking, sir.
Sir, sir, somehow.
Sir, you are not audible.
Hello, hello. Am I audible now?
Yes, sir.
Yes,
Yes.
sir.
This net is creating this problem. Internet connection is very poor here.
Sir, are you in college?
Yes. Hello. Is it okay now?
Yes, sir.
Yes, sir.
Okay. So by using this voltage control method, that means by feeding variable voltage generated by this generator, we can control the speed below rated speed, and by varying this rheostat we can control the field flux of this motor, thereby changing the speed above rated speed. Okay. Any question up to this? And since we are applying both terminal voltage variation as well as field flux variation method, so we can change the speed of this motor over a very wide range. That means from a very low speed to a very high speed. Okay. Any question?
No, sir.
So note down this question, that is what are the advantages and disadvantages of this method, that is Ward Leonard method of speed control. Okay, can you tell me one disadvantage right now? It is very obvious. By seeing this schematic diagram, you will be able to say, I hope so. Just one disadvantage.
Two generators are required.
Not only two generators, we require 3 electrical machines to control the speed of one electrical machine only. So it is not very economical, right?
Yes, sir.
Okay, rest you will read from any book. So speed control of DC shunt motor by varying the resistance in series with the armature circuit. So this method is very simple. Here we have connected one external resistance known as the controller resistance RC. So depending on the value of this RC, we will have different IA value. Okay. Now remember one thing, that this IA will change only for a very small period of time. That means during the transient only. Okay, when the motor reaches its stable operating speed, this armature current will be same as that of the previous value. Okay, so that we will see later on. Let us see. So in this method of speed control, we will be using one external resistance known as the controller resistance, which is connected in series with the armature circuit, armature winding. Okay, as shown in this schematic diagram. So here Vt is the applied voltage, Ra is the armature resistance, Eb is back EMF, and since we are applying constant voltage across the armature, so voltage applied across shunt field winding will remain same, so flux will also remain same. Okay. So suppose when the value of RC is 0, okay, or RC is not present in the circuit, then at that condition the armature current value is suppose IA1. I'm so sorry. And it is given by this equation, IA1 is equal to Vt minus Eb by Ra. So this is IA1, this is the initial value of armature current, which we can write as Vt minus K phi omega M1 Ra. So here for this value of armature current, the speed is omega M1, because the other parameters are constant. Now, when RC is introduced in the armature circuit, that means it will have some non-zero value. Then what will happen? Let us assume that armature current is Ia2. Okay, and that Ia2 is given by this equation Vt minus K phi omega m1. Observe the speed, it is still omega m1, because though we have increased the value of Rc, but due to inertia the rotor cannot increase or decrease, that means change its speed instantly. Its speed is still omega m1, but the current value has changed. See, current is an electrical parameter, whereas omega m, that is the speed, is some mechanical parameter. Okay, and any electrical process is faster than any mechanical process. Okay, so as soon as we have changed this RC value, the current will change, but the speed cannot change so quickly. Okay, so that is why the expression of Ia2 contains the speed, previous speed omega m1. Okay, is it clear? Any doubt?
No.
No, sir.
Now we know that Vt by K phi omega m1 divided by Ra is actually Ia1. So we can rearrange this expression. So this is basically equal to Vt minus Ka phi omega m1 by Ra into Ra by Ra plus Rc. So this is basically Ia1. So we can write this equal to Ia1 into Ra by Ra plus Rc, isn't it? Now tell me which current is having higher value, Ia1 or Ia2?
IA1.
Obviously, because this ratio is less than 1, isn't it? Ra by Ra plus Rc, this is obviously less than 1. Okay, so Ia1 is having higher value, so Ia2 is less than Ia1. So what will be its effect? Sorry, Ia2. What will be its effect? Its effect will be a reduction in the torque. Suppose when armature current was Ia1, the torque was, see, this is not the load torque, this is the developed torque. Okay, load torque is constant, TL, that is constant, whatever load is connected across, I mean with the shaft of this motor, that remains fixed, but the generated torque, that can vary depending upon the variation of flux or armature current. For DC shunt motor, our flux is fixed, so we can vary the armature current. So depending on the value of armature current, we can change the value of developed torque. So when armature current was Ia1, the developed torque was Ka phi Ia1. Now as the armature current has reduced due to this insertion of this Rc, so new developed torque will be Ka phi Ia2, and obviously this Ka phi Ia2 is less than this Ka phi Ia1. So suppose this is Te1 and this is Te2. So Te2 is less than Te1, right?
Yes, sir.
Now if Te2, initially the motor was running at stable operating speed, which means this TL was equal to Te1. Okay, now the developed torque has reduced to Te2, which means this TL is greater than Te2, right? So what will happen? If the load torque is greater than whatever torque is developed by this motor, what will happen? Suppose you have a capability of carrying 50 kilogram, okay, and you are given 100 kilogram to carry. What will happen?
fall down.
Yes. So here the speed will fall, omega m will reduce, right? Because the motor is not able to generate so much of torque, so speed will fall. Now if speed falls, what happens to EB?
False.
Yes. Now if EB falls, what happens to current? What happens to current if EB reduces?
Sir,
Increases.
increase.
Yes. Now current cannot increase infinitely. It will increase to such a value that thereby increasing the developed torque to get a stable operating point. So this current will goes back to IA2 to IA1 because it has to develop this TE1 amount of torque. Okay. So in this way armature current remains same. You got my point?
Yes.
Yes, sir.
So speed has reduced but keeping armature current constant. This is very important. Sorry. So omega m1, that is for armature current IA1, and when RC is introduced, omega m2 is given by this expression. See here the current value is IA1. So don't get confused. This current has to be IA1. Oh sorry. Got my point?
Yes, sir.
So after transient, that means after reaching the next stable operating speed, the armature current gets back to its previous value. Okay. So therefore this was our back EMF when there was no RC or RC was equal to 0. Now the back EMF is EB2. This is our current back EMF value when RC is having some non-zero value, but the armature current is same. Okay. So now observing this expression and this expression, we can compare this EB1 and EB2. So tell me which one is greater?
You1.
So EB1 is greater. Therefore, since EB1 is greater than EB2, so obviously this omega m1 is greater than omega m2. That means by changing the value of RC, we can change the speed of this motor.
Yes, sir.
So that is how we control the speed of a DC motor by inserting some resistance in the armature circuit. See, though we are inserting some some resistance in the armature circuit, so it is very common to think that this armature current value will change. But since the load torque is constant, this armature current cannot change. Initially, it will change, and and it will come back to its previous value as soon as the motor reaches its stable operating speed. Okay, is it clear?
Yes.
So omega m1 by omega m2, sorry, omega m2 by omega m1, that means this angular speed can be replaced by its equivalent rotational speed, that is sorry, in speed in RPM or RPS. So N2 by N1, that is also equal to EB2 by EB1. Okay, so based on this equation, we can draw these different speed torque characteristic at different RC value. So when RC is 0, this is the normal speed torque characteristic. When RC1, when we consider the value of RC as RC1, then this is the normal operating, this is the characteristic speed torque characteristic, and this is the normal operating point, stable operating point. If we further increase the value of this external resistance, the speed will further reduce. So when for RC2, the stable operating speed is this. Stable operating point is this. Corresponding speeds are this and this and this, and this is the no load speed. Okay. So in this way, we can control the speed of a DC motor by varying the resistance value connected in series with the armature circuit, and by this method also we cannot increase the speed above base speed. Here there is no option of increasing, but in our previous method, that is the variation of terminal voltage, in that method we have the option, but we cannot do that due to some protection point of view. Okay, but in this method we don't have any option to increase the speed above base speed by varying this controller resistance or external resistance. Why is it so? Why we don't have the option? Anyone? This is very simple. We cannot reduce the value of RC below 0. Okay, RA is fixed, that is the resistance of the armature winding, so you cannot decrease that value. So for this value we will get the base speed. To increase the value speed using this resistance control method, you have to decrease this resistance. Okay, so for that you have to connect some negative resistance, so that is not practically possible. Okay, so in this method we don't have any option to increase the speed above base speed, but in our previous method we have that option, but we do not apply that from some protection point of view. Okay. Okay, time is over today up to this.